In this video, we're going to work on day 2 of the 2.5 optimization homework, and we're going to start with question number 2. So it does tell you to read your textbook beginning in section 2.5. You want to get used to reading a textbook and looking at examples and working them through, because sometimes, especially when you get to college, you're going to be assigned a section of a book that you're responsible for, and if you've never read a textbook, it's going to be an eye-opening experience. So start working on reading our textbook. You have it online, so you can definitely do that. Okay, so this says, if you are in the house throwing a ball up in the air in a parabolic fashion, such that its movement can be modeled by this equation, so here's our equation, find, using calculus, the CV, so the critical value, that will maximize the height of the ball. So I'm looking at that. It's a parabola, and it is downward facing with a starting point at a y-intercept of 3. That's what I'm looking like. I know that where the slope is 0, that's where my x critical value is. Okay? So I'm going to now identify the critical value. So let's start that. So this is the A part. So f prime of t equals negative 8t plus 16. Second derivative equals negative 8, just like I thought. And what that tells me, it affirms that I have a downward facing parabola, which means it's always concave down, and therefore that denotes a max critical value. Okay, set your first derivative equal to 0, and I find that at time equals 2 seconds, because they gave me time, I'm going to give them back time at this point. So at 2 seconds, the ball's at the highest point. So reading part A little bit further, it says, once you have identified the CV, build a sign chart and use it to illustrate a first and second derivative test. Okay, we could do that. Here's your sign chart. You put 2 here. This is your slope. This is your function. This is your second derivative. Okay, if you take the 2 and plug it in, if you take actually a value to the left of 2, so let's take 1 and plug it in your first derivative, you'll get negative 8 plus 16, which is positive. If you take 3 and plug it in, you'll get negative 24 plus 16, which is negative. Therefore, your function goes up and comes down. And if you test right at 2, you're going to find that you get a negative for your second derivative, and that looks like that. Okay, so that's my whole test. Excuse me, write an explanation of your sign chart indicating what the first derivative test indicates, using the word slope, and what the second derivative test indicates. Use the word concavity. Okay, so f prime of t, the slope, changes from positive to negative at xcv equals 2. Therefore, at 2, we have a max. Okay, so that's your first derivative test explanation. So let me erase that. And we will do the same thing with my second derivative test, but in the light of space, I'm going to conserve it this way. So your second derivative test would be f prime prime of t is negative at xcv equals 2, so therefore we have a concavity that is down, which yields a max. Okay, so those are your 2 statements that I would say. Provide a sketch. We've done that up here, but now instead of having just the phrase XCV, I'm going to erase that and we'll write in again the 2, because that is what our CV is. Okay, so then they go on in question B, and I'll change color. Okay, question B, if the height of the ceiling in the room is 20 feet, will you hit the ceiling before you reach the maximum? Or at the maximum of the ball's trajectory, or never? How do you know? All right, so what do I do? How about if we figure out at f of t, where t is 2, what is our height? So -4 times 2 squared, that's going to give me -16, plus 16 times 2, that's 32. So this is -16 plus 32 plus 3. So that's 16, 17, 18, 19. So it looks like my max is 19 feet. So right here, where the CV is 2, my max is right here at 19. So will I hit the ceiling? And the answer is no. How do you know this? Well, our maximum height is only 19 feet. We'll never get above that maximum height if we keep throwing it in the same fashion. And so therefore, my ceiling is safe. I will not be hitting the ceiling based on my analysis in Part A. Okay, so having the sketch, having the point of 19 identified, and then what you could even do is you can plug in, go a little further up, and give yourself y equals 20 here, so that you can indicate that you're never going to hit that ceiling. Okay, and that takes care of that problem. Let's move on to problem 2 in this day 2 section of the 2.5. Okay, in question number 2 here, it refers us to example 3 in the textbook on page 181, and that's about a rectangular garden. So you should definitely look at that, but I'm going to answer this question on this slide. So it says, given 80 feet of fencing, find the maximization of the area of your garden when you use your house for one side. Okay, so what's happening here is you have to understand what example 3 on page 181 was doing. So we have a house here, and I'm going to make a garden right over here. Okay, so hold on, let me just get my pen to work. We'll change colors. Okay, hold on. A little technical difficulty here. Okay, fix that. Okay, so here's what's going on. The garden initially, since you know it's a rectangle, these sides will be the same variable, and this one will be a different variable. So our constraint is the given. So that's kind of like saying if. So if we have 80 feet of fencing, given that we have 80 feet of fencing, so my constraint is that the fencing is going to go around this garden. So x plus y is going to equal 80. Okay, so that's going to be 2x plus y equals 80. Okay, find the maximization of the area. So your objective function is still to maximize the area, which we know is length times width, or xy. So area equals xy. Here my area has two variables, so I'm going to switch out the y, and I get y equals 80 minus 2x. So x times 80 minus 2x is going to equal 80x minus 2x squared. Okay, take the first derivative. A prime equals 80 minus 4x. I'm going to go ahead and take the second derivative, minus 4. Since the second derivative is minus 4, I know that I have a maximum when I use the CV I get from setting my first derivative equal to 0. That CV will be 20. Okay, so right now I know if I set my first derivative equal to 0, my x CV will equal 20. And here is where I got that from. Okay, so they want to know a lot of things here. They want to know to find the maximization. So if my x CV equals 20, what does my y equal? Well, plug your y, find your y by plugging in your 20 right there. So 2 times 20 is 40. 80 minus 40 is 40. So my y is going to be 40. This is in feet. This is in feet. So those are my variables. The maximum area will be the product. So x times y is 20 times 40. So therefore my area will be 80 with another 0, so 800. Okay, so let's get our little sign chart. So we know that our CV is 20. Up here I'm going to put my A prime, and then my A, and then my A prime prime. Okay, so if you take your slope of your area, which is right here, and I plug in 19, so 4 minus 19, 80 minus 4 times 19 will be a positive. If I plug in 21, 80 minus 4 times 21 will be a negative. Therefore, my function is going to go up and then down. And I already know that the A prime prime of 20 is negative, and therefore my function looks like that. I would then say in this little box, which I'm not going to write, that because the slope goes from positive to negative at the critical value of 20, and because the second derivative is negative at the critical value of 20, I know that my x will generate a maximum area. So the critical value of x equals 20 generates a maximum area of the garden, and that maximum area is 80 feet squared, and also the y will be 40 feet. Okay, so that's that problem. Let's go ahead and we'll do the next problem, which is number 3. Okay, number 3, they're going to have us do the exact same problem, but now we're not going to use the side of our house. We're going to use the entire garden as a freestanding structure. So therefore, when I do my sketch of the problem, I can now have 4 free sides. And you should remember that when you have 4 free sides, you're going to probably get a square. Okay, so my objective function is still xy, is the area. My constraint is now I'm going to use those 80 feet of fencing, and I'm going to spread it over what? 80 will equal x plus y plus y, the entire perimeter. So that's going to be 2x plus 2y. So we're going to switch out our y. So 80 minus 2y equals 2x. So therefore, if I divide by 2, I end up getting x equals 40 minus y. Okay, I need that because my objective function was written in terms of x and y. Now I'm going to write it in terms of just x by plugging in 40 minus y. So, 40 minus. I don't want to do that. I want to reverse it. So I want to, let me just backtrack a little bit. I'm going to erase this, and erase this, and erase this, and erase this, and erase this, because I want everything to be in terms of x. So I say 80 minus 20. Okay, hold on one sec. Okay, so 80 minus 2x divided by 2 equals y. So therefore, y equals 40 minus x. Now we're cooking. Okay, so a is going to equal 40x minus x squared. A prime, therefore, equals 40 minus 2x. A prime prime equals minus 2. Therefore, we still have an indication that my function is concave down throughout its domain, and therefore I'll have a max. And next I want to say, what will my x be now? Set your first derivative equal to 0. 40 minus 2x equals 0. X will be 20. So x is going to be 20 feet. Since y equals 40 minus x, 40 minus 20 is also 20 feet. I do indeed have a square. My area this time equals 20 times 20, which is 400 feet squared. So my garden's going to be smaller, which does make sense because I have the same amount of fencing and I'm not using the house as one part. So that's my scenario. My area looked like, let's see, area equals xy. So it looked like this. Here's my area. Here's my critical value. Here's my x. That was 20. My max was 400. And then I'm going to leave it to you to go through and do a first derivative and second derivative test to indicate that you have indeed maximized your function being the area. Okay, so that's a pretty good overview of all that we're going to have on the quiz. We have 2.5 in the bank now. There are more complicated problems in 2.5, but we'll do them later. So you should have the same answers I have, and I hope that my explanation was sufficient for your purposes.